Imagine if you could look at a random splash of seawater filled with tiny extraterrestrial creatures. We could find something as super positive as that in the plumes. How does that influence how we can explore? Cassini has sampled the plumes already with no chance of contaminating the oceans, a gold star for planetary protection. So Enceladus is a sure thing. Its plumes erupt continuously, feeding Saturn's E-ring. Europa's plumes are much more uncertain. They may be sporadic, like this Icelandic geyser, and fall back to its surface right away in the higher gravity, making it more of a challenge to sample them. The plume Hubble saw could be the result of a large meteorite. So I'll focus on Enceladus for now, but this also applies to Europa if we can sample its plumes. The ocean is kept liquid by eccentricity tides. Enceladus can't go into a circular orbit because of resonances with Dione. Its heat budget is long for standing puzzles. Some models work, but we don't know if they are valid. Evidence from earlier frozen over tiger stripes suggests it may be freezing slowly. We don't need to worry about the next few thousand years, but the geysers may stop within 200 million years. The same evidence suggests its ocean is at least 1 billion years old. Its interior is probably like a carbonaceous chondrite meteorite, unprocessed early solar system material, rich in organics. That's great for life, except that it's also completely undifferentiated and porous. It's thought that all the salt from its interior has already flowed into its ocean. So any life might have run out of food and be extinct or very sparse. On the other hand, tidal effects might easily supply enough energy for a complex ecosystem. Cassini's measurements suggest two main possibilities: a very alkaline soda lake or a less alkaline white smoker type hydrothermal vent. Or its ocean might be very young, only 1 billion years old, or perhaps life evolved more slowly. If so, perhaps it is only the early stages of life, or no life. There's a tendency to look at this and say the right-hand side is what astrobiology is all about, complex life. And in the case of the left-hand side, let's leave it to the planetary geologists. And for that matter, we might feel that we have a duty to bring Earth life to a lifeless ocean. I'm going to suggest that early life or non-life is also of extraordinary interest for astrobiology, and as well as that we have nowhere near the understanding needed as accidental or intentional planetary ocean eco-engineers. This visualization shows how Earth life makes proteins. Here, messenger RNA, produced by DNA polymerase, meets a ribosome, a huge molecular machine that spontaneously assembles around it. These green transfer molecules each bring a single amino acid to the emergent protein chain. You can see the amino acids as red dots at the tips. This is going on at this speed in every cell of every known Earth creature, and the visualization just hints at the complexity of the process. It works, but seems Heath Robinson or Rube Goldberg if you're from the States, like the professor's potato peeling machine. Life must have been started simpler, perhaps as a self-replicating polymer not yet alive but encoding information, or perhaps an autopoietic cell takes in ingredients, uses them to recreate its metabolism and cell wall, and expels waste. It's only a dozen or so chemicals, and it just splits when it gets large enough, or a daughter cell from inside escapes. This shows time of origin against gene complexity on a log plot. Prokaryotes, cells without a nucleus, are oldest. Continue the line back, and it crosses the axis at around double the age of the solar system. So, perhaps life started on an exoplanet around an older star. This passes through a nebula where our solar system was forming in one of these fingers. It misses most of the embryo stars, but by chance comes close enough to ours to transfer life by meteorite impacts. It can do this from quite a distance. Here, Earth would be forming in one of these dark bands. Or, the solid line may show the slope for DNA with error correction. Perhaps earlier on, life evolved more quickly, as shown in the dotted line. Life in these extraterrestrial oceans could be anywhere on this graph, even the likes of fish and octopuses in the oxygen-rich ocean of Europa. It's unlikely we have both reached exactly the same stage. Modern multicellular life on Earth is quite recent, so what is the chance it has evolved some future life on Europa that we don't have yet? It could as easily be back there or it could be up there. Perhaps 50-50. And if it got that far, what about a civilization likely to be millions of years old, in an ocean, no fire, their technology would be limited. They would know nothing about us, and we would know nothing about them yet. Then in the other direction, it could be somewhere in the first half of the graph. More than half of evolution is hidden from us. Each pixel covers over 70 million years, so our lab experiments, like Urey Miller, explore a tiny fraction of the very first pixel in this graph. That leaves a huge gap, which must have steps as momentous as the development of the nucleus, multicellular life, plants and animals. But what those are down here, we can only guess. In some ways, that might be the most interesting outcome of all, to fill in a little of this gap. That is why I suggested an early or non-life ocean could be just as interesting for astrobiology. It could have evolved quite a long way as non-life, but it's getting more and more complex. If life evolved around a previous star, there's a chance that it's related with a common ancestor older than prokaryotes. But if the ocean is young, or life evolved gradually, it's likely to be independently evolved, especially as there's little meteorite transfer, as you can see. Earth life seems optimal. It stopped at 20 main amino acids, and that's with a lot of spare coding capacity, as you can see. Here, serine is coded in 4 different ways, for example. Each of these triplets could easily have coded for a different amino acid. However, this could easily be a local optimum. Let's think of the height in this map as anything you want to optimize, such as the efficiency of the metabolism. You start in Australia and keep walking up, and you'll probably just get to the top of a small hillock. If you allow yourself to go up and down and travel great distances, so that would be with quantized annealing, for instance, the highest peak you reach is only a little over 2,000 meters high, less than half the height of Mont Blanc. If you're at the very top of this peak, because it's a summit in this analogy, any tweaks such as adding more amino acids always take you downhill, so you might well think that Earth life is the best that any life could possibly be. But if you started in North America, you'd end up at the top of Mount McKinley, which again would be a summit and seem totally optimal unless you were able to explore as far as South America. And then both of these would be a lot lower than Mount Everest, which you would reach as you gradually explored Eurasia. So there could be many different optimal best solutions for life, and we know of only one. Here we are looking at the workings of the oldest cells, such as the prokaryotes in this analogy. So what's more, the life on Enceladus could be much better than us at metabolizing. It could be the Mount Everest of primitive cell metabolisms. Or our metabolism could be Mount Everest, and life on Enceladus is relatively feeble. Since we're just looking at the interior of the cell, the early cells, there's no way of knowing if Enceladus does have life. Perhaps 50-50 that is better than us. Specialists who study the interior of a cell sometimes compare the complexity of the interactions to an ecosystem. In this analogy, all Earth life has the same ecosystem inside. I've listed a few of the things in it, but experts could add many more, common to all Earth life. This ecosystem is so similar, life forms often swap genes in parallel transfer, and they still work. Here, a gene from a fungus gave this pea aphid the ability to generate carotenoids, which turns it red like a carrot. Imagine if the African savanna was the only ecosystem biologists knew about, with minor variations. And then one day, we discover a coral reef. We have never seen a tropical rainforest, or tundra, or the seashore, or anything. This is how much we could learn, just from observation of a single cell or photocell based on different principles. So, of course, we are careful. This is one of the Viking landers' gold standard of planetary protection on Mars. Nevertheless, you can question if it was sterilized enough. The aim was to have no more than a 1 in 1,000 chance of contaminating Mars during the exploration stage. Is that enough, given that it could be a super positive outcome? Anyway, that decision is made, and it is generally thought that we have not contaminated Mars with Earth life, mainly because conditions there are so harsh. But it's important to know that we haven't yet looked at our spacecraft to see how many dormant microbes there are, and in what species, not on Mars. Our calculations predict that there are microbes, and that they're sitting there doing nothing. Again, we don't know for sure, because we haven't checked to see if our spacecraft have replicating life around them. For instance, Phoenix crushed with the advancing winter dry ice sheet. We have no experimental data from Mars on this. So, this is a little bit shaky. We don't think we have contaminated Mars, but it's not the best basis for making decisions about ice moons. The National Research Council looked at it, and especially since these oceans are so much more habitable than Mars, and probability assessments are more uncertain, this approach just wouldn't work. They recommended binary decision trees. The orbiter, or flyby, passes the test at stage 5 with a yes, because it's not going to encounter a habitable region. But any Enceladus ice mold penetrator or cryobot passes all the way through to the last step. Then you have stringent planetary protection, or cancel mission. The Russians in Antarctica drilled nearly all the way down to Lake Vostok and then discovered they were approaching a lake. So they just stopped for over a decade. Eventually they drilled down into it in such a way as to trigger a mini geyser of 30 or 40 meters so that there could be no forward contamination into the lake. This is like a flyby mission. So far they have only sampled the plume. It would be easy to send a submarine down, but they feel we haven't yet got the technology to sterilize it. So in the same way, when exploring Enceladus, we should always have the option cancel the mission, not ready yet. This rabbit-proof fence was built to protect Western Australia in the 1900s from rabbits introduced by European colonists. It was the longest set fence in the world and worked after fashion for some years. Cartoonists had a field day, showing here a probable use that rabbits might make of the fence. What kind of fence could we put across the Enceladus or Europa oceans? COSPA recommend a target of a chance of 1 in 10,000 of contamination in the next 1,000 years. However, there was a lot of discussion in the workshops. There's no science you can do, no a priori calculation, no experiments that can give you these numbers. It is an ethical decision. If you think about it as a potential super positive outcome, you might look at that a bit differently. We have a chance of a super positive outcome to billions of people revolutionizing medicine, agriculture, nanotechnology. We don't know how probable it is, but it is a possibility. In the direction of sample return to Earth, the legal situation is clear. This is a guideline of modern international law introduced because of the new things we can do. A sample return could, in the worst case, cause degradation of the environment, for instance if we return a life form better metabolizing than Earth's life. In a situation like this, we must take precautions, even if we don't know what's in the sample. It's no good saying, I've no idea, but surely it's okay, or use hand-waving arguments. We have to take precautions anyway. And it's us, the proponents, that have to do the science. And the discussion has to involve all affected parties, which here may mean the entire world. We can never say, we are the scientists, we will make the decision for you. And you have to consider all possibilities, including always no action. That can get forgotten. If you ask experts, how can I return this sample safely? That's the wrong question. They must always have the option to say it is not safe yet, if that is what their research shows. I suggest that it should be the same for super positive outcomes in the forward direction. We should take precautions even though we have no idea what is there. As proponents, it is up to us to prove that what we are doing is not going to impact on it. And I would say because it is super positive, it impacts on the entire Earth because of those billions that would be affected in the best case. So it should be similarly open and involve discussing all possibilities, including again no action. Here I have just adapted the first sentence of the wingspread text, one of the statements for the precautionary principle, to show the idea. Change harm to health and or the environment to a super positive outcome, and you get a reasonable guideline in the forward direction. Carl Sagan once said about a sample return from Mars, you can't take a small risk with billion lives. Nick Bostrom has developed a philosophical approach to existential risks, that is to say risks of serious impact on human habitability of the Earth and our future life prospects. He has suggested that we haven't evolved with the same intuition because obviously we haven't encountered them before. He suggests one way to get a clear idea is to look at the expected number. So for instance, in a sample return discussion, they often say that the risk of 1 in a million is acceptable. That's a tiny figure used as standard for biosafety laboratory designs. But if you multiply that by the population of the Earth, the expected number affected is 7,300, and that becomes millions or trillions of people if it is possible that all future humans could be affected. So even with a tiny chance of 1 in a million, sometimes the expected number impacted can be huge. I suggest the same applies in the forward direction. There's absolutely no impact on human health, but if you increase the chance of a super positive outcome by 1 in 10,000 by taking more care and do the same calculation, the expected number is 730,000 people benefited. and again it becomes billions or trillions if you consider future generations. Here, possible future beings from Earth study Enceladus. At bottom left, H.G. Wells' human for a million years in the future, little more than eyes and a brain, because machines do everything. Then, the humanoids from Avatar, standing in for the idea of future humans more closely connected ecologically with the Earth. Then, there's Alex the grey pigeon, possibly the most intelligent non-human known. Perhaps in the future, we may get civilizations of descendants of parrots and other creatures, either coexisting or following on. Over the next 500 million years, surely thousands of such civilizations will arise and fall, and some of them will come and visit Enceladus. We have a super positive outcome here for all of them, not just ourselves. Also, of course, for any beings in the oceans already. This is the next step up from a flyby, an orbiter. In the plans, it starts with several gravity-assist flybys of Titan, then the inner moons, and then it ends up in an equatorial orbit around Enceladus with almost no total delta V. Sadly, the polar orbit is unstable, so it can only pass through the geysers at its south pole occasionally. But the big advantage is that it can capture the material at around 100 meters per second. This is only 8 times faster than Usain Bolt. With capture into aerogel, we can hope to find even viable microbial spores and intact autopoietic cells if they exist. You might think every sample would be the same. However, we'd be able to fly at different heights, for instance go lower for the larger particles, which Cassini has already done. Also, go through plumes at different states of the tides and sample the plumes individually. And if there's life here, perhaps sporadic subsurface events equivalent to algae blooms send interesting material into space from time to time. You get a rather poor idea of what we can do in situ from our mission so far. Only one of these instruments has ever flown, the Philae Cossack chromatographer, chiral gas chromatographer. We can send sensitive labs on a chip, able to distinguish just one molecule of an organic in the case of subcritical liquid water extraction. This is now miniaturized right down to the astrobionibbler. Monoclonal antibodies can also be very sensitive. Solid 3, in its tests in the Arizona desert, found a previously undiscovered habitat 2 meters below the surface. Incidentally, it is not limited to Earth-based organics. The key to Cassini's success was to send a wide range of in-situ instruments. Nobody expected plumes, but it was so well equipped it had what was needed to get started. I suggest we do the same for our search for life. This can help invigorate the field. Many teams of astrobiologists will see instruments fly in space for the first time since Viking. And even if they don't find anything, for instance, if the miniaturized informational polymer sequencers don't find any DNA or XNA, this may tell us that it is not related to Earth life, and rule out many other alternatives as well. Or, if the microbial fuel cell finds no redox reactions, a null result can be significant. Many of these experiments are so small nowadays, far smaller than for Viking, we could maybe even send all of these. I would suggest a good high-res optical microscope as well. Think how silly it would be if there was life in our sample moving around purposefully and we just couldn't see it. This shows the next stage. You might think that there's no chance of contaminating the ocean with an ice mold because the geysers erupt upwards. But the cracks continually open and close with the tides, unfortunately, on every orbit. Also, new geysers must form from time to time. It could get crushed or work its way down, or parts of it could. Notice also that the interior of the geyser is a near vacuum filled with water vapour for a long way down. How we sterilise it may depend on what we find. For instance, if the ocean consists of autopoietic cells, we may need to take great care not to introduce even dead machinery of Earth life, in case the cells take it up and learn new tricks. Or, if it is closely related to us, we may need to take care about GTAs, which can transfer genes rapidly even overnight in seawater to completely unrelated phyla of Garcia. With ideas of a super positive outcome, we need to sterilise the ice mold totally, not just for the next 1,000 years. I think that could be feasible. With ExoMars, they are exploring carbon dioxide snow. As temperatures above 31.1 centigrade and high pressures, CO2 becomes supercritical, a state between a gas and a liquid, penetrates cell walls and dissolves organics readily. When pressure is reduced, the organics are blown away in the snow by hot dry air, leaving nothing behind. That's assuming it's been cleaned a fair bit beforehand. We would need to sterilise any electronics at the end of the mission, perhaps by the same method as it has been used successfully to sterilise USB drives, or perhaps with ionising radiation. Even if we solve the sterilisation issues, I suggest that our first mission looks at the plumes with as wide a range of instruments as we can possibly send. Because until then, we can't do an optimal design for our ice mole, and we won't even know what are the best instruments to put on it. If we get interesting results, it will surely be easy to get funding for follow-up missions. By then, our spacecraft may be able to get there quickly, drill more quickly, return samples sooner and have smaller and better instruments. As for sample return, that needs a new talk, but in short, you might be surprised at how complex the suggestions are for planetary protection for a return to the Earth's surface. It would add over $500 million to the cost and may still leave some safety questions unanswered, as well as requiring about a 10 years process of new internal and international legislation. I think the safest, simplest and also lowest cost place to return to would be to a teleoperated facility in high Earth orbit, which humans go nowhere near. I have detailed reasons which I can explain separately. Anyway, we wouldn't know for sure how to design the return capsule until we know what we need to return, where to return it from, and how to best preserve it on a long journey back. Instead, I suggest we get the ingenious teams of astrobiologists to submit the ideas for instruments to search in situ, and send the very best of these on our next mission to look at the plumes close up.